My goal here is the following. You're only 17, right, in this class, as far as I know. So I see no obligation as to try to have a specific distribution of grades in this class. The sample is too small, that's what I mean. When you have 100 people, well, statistics picks up. So it was more than 1, 3 at least.
And I mean, we all pick these Cs, so we're obviously above average intelligence.
Of course. Oh, by the way...
Speak for yourself.
I mean, average intelligence, I don't know, that's... Well,
Yeah.
you just need to drive along and that's it. That's it.
50% of the people are dumber than 600.
Yeah, I mean... Okay. All right. So what I was trying to say is I have no problem if everybody writes an A, right? I wish you all write an A or whatever, A plus, whatever is the highest. You're going to get numerical scores. I'll tell you at the end roughly what the questions are so you know what to prepare. I just have to tell you up front though, because the questions, pretty much most of them, if not all of them, are pretty straightforward. If you're going to make mistakes, they're going to be fairly straightforward mistakes. So just, if you're like me, I will double check every answer. The other unfortunate part is I'm not in town tomorrow, so it's going to be Alberto and Ali, all right? But they do have my phone number. If you need to talk to somebody and they cannot give you a fair answer, you feel free to call me. I think by that time I should be available on the phone. Right? Okay. Sorry, this year is very weird in terms of travel. I never had this much travel in the semester. And usually when I schedule this class, I tend to do it 1 hour and 2 hour lecture as opposed to 3 1 hours. That gives me some flexibility. Also, I think it works a little bit better because there are some material that's better to have continuity for 2 hours, like this one. But anyway, I neglected doing this year. Okay, so I'll talk at the end about the midterm.
This won't be on the midterm, right?
Huh?
This won't be on the midterm?
Oh, there can be questions that is, how about you do something you haven't done before to see what you can do? But no, it's not going to be on the midterm. No. Anyway, so I think there's one person missing at least, right? From the audience. Okay, anyway, so we're going now, so welcome again to the class. Thanks for making time as always. What are we doing now? We're switching hats and so far we've been programmers and we're saying, how can we convince them, what does the machine do? I don't care how it works. I just want to do something with it. It's like driving a car, right? To be a very good car race driver or whatever, you don't necessarily need to understand how to build an engine. You just need to understand how it behaves. So now we're going the opposite. We're trying to build an engine. This doesn't mean that you're a good programmer. It just means you're a good designer. Same thing for the car. You can design a perfect engine, but you might not be the best driver in the world. These are two different kind of skills. But you've got to understand the interface. Are we now complete? Are we whole? Okay. All right.
We're missing 2, but we're missing 3.
2. We're still missing people. Okay.
I don't think they're coming.
They're not coming?
I don't think so.
Oh, I am disappointed. Anyway, I'll survive. Okay, so we're going to start talking about how to build a processor. We're going to do 3 different implementations of a processor. The first one is the simplest to understand. Right? It's not going to be the highest performing one. And it's going to be like a stepping stone to get to the other ones. We're just going to build a processor that works. At the end, it's going to boil down to this. Now, I gave you a piece of paper. You didn't get one. This is the definition of a processor. I want you to trust me in this now. Mark my words and trust me when I say this. We're not doing news. We could have done news. Right? The problem is that if you do news, because of the length of the class or whatever, news has, even though it's a fairly simple machine, it has a lot of instructions inside. If I wanted to cover the whole news, we'll need a lot of lectures. There are 2 problems with that. First of all is we don't have the time in the lectures. Second of all, after a while, you're going to be all saying, come on. I mean, I really understand how this is done now. We're just going over the stuff, these things over and over again, and I'm not getting anything new. I could have done this on my own. Instead, we're going to define our own little CPU. It's a toy CPU that is not like a super duper design or anything like that. It's designed so that we can go through the whole design. I can draw the whole thing. I can show you this is how you do the whole thing. Furthermore, when I did the CPU design, I made some decisions in the instruction set that will allow us to expose things that wouldn't have happened if I were doing news. Right? There are some decisions that are not the best decisions on earth, and these are intentional here. They're not by mistake or anything like that. It's so that we can illustrate by decisions you make when you design the instruction set. You can influence your implementation. You can make your life miserable one way or another. Okay, so at the end, when we saw the first implementation, we're going to end up with something like this. This is half of the design. And I don't mean in terms of half, in terms of this is how much area or complexity like that. This is only a portion of it. This is what we call the data path. One way to view a processor is it has the data path, and then it has the control. What is the data path? The data path is a circuit that can implement, can do the actions necessary to execute any instruction. I need to do an addition, this can do an addition. Read two registers, add them together, blah, 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 blah. Do I need to do a load? This can do a load. Do I need to do a store? It can do a store. What this cannot do is cannot decide what to do. It can do anything at any given point in time. It doesn't know what to do. So this is like a puppet, right? You can make it take any stance you like. However, you need a puppeteer that decides what needs to happen right now. That is the control. We're going to spend a lot of time first on the data path, and that's going to most of the complexity is going to be in this design. And then we're going to do the control. It's going to turn out the control is fairly straightforward in this case. But this is going to be obvious in retrospect, not in the beginning. There's no value in that right now. So for the time being, I want you to think, all I care about is to build a design, a circuit that can implement any instruction. So for this, I will assume you know digital design and you know some fundamentals. I will review some of them, but it's going to be a fairly straightforward, fairly superficial review of things. I will assume you know. If you don't, you can ask me to give you pointers, and you can also go back and look at the previous course that you took on digital design. I will assume you know what an XOR gate is, what an AND gate is, what registers are, stuff like that. And I will be drawing blocks. That's how you can do designs like that. If I were to show every single thing in minute detail, we're never going to finish. Everybody okay with this? All right. Now, let's talk about our processor now. Wonderful. This is a very powerful machine. It has 256 bytes of memory. Actually, it's going to have two memories. One is going to be a data memory, and the other is going to be an instruction memory. This is slightly different than NEOS. NEOS has one memory, which is used for both instructions and data. Our machine is going to have two separate memories. Right? One of the earliest machines built was like that. This is called a Harvard architecture, because I guess it was built at Harvard at some point. It did have two memories. Most processors today, very close to it, to the processor, the physical level, they do have two memories, but they're hidden from you. So it's not that what we're doing is junk and not useful. Actually, this is how you build processors today, but this is hidden from you. So two memories. Each one of them is going to be 256 bytes, and it's going to be byte addressable, which means that addresses are 8 bits too. Now, what comes after that? There are a total of four registers, and each one of them is a byte. Okay? Why 4?
Because you decided.
Exactly, right? Because somebody decided that's why it is. There's a reason why it's 4, because the instruction encoding becomes easier this way, but that's the way to approach it right now. In addition, there is an unfortunate register called program counter again, rather than instruction pointer, who has been a better name. This points to the next instruction in memory to execute. It's also 8 bits, because the address space is 256 bytes, okay? Now, this is something that NEOS doesn't have, but other machines do. This is one way to introduce you to this concept. There are also two single-bit registers called 0 and negative. These are called condition codes or flags. x86 has it, ARM I think has it too. Don't quote me on that, but x86 definitely. x86 I mean AMD processors, Intel processors. They have this kind of, it's a different way of doing branches, and I'm going to explain how it works. That's one way. These are single-bit registers. We're going to have that. What else do we have? Let's see. And there are roughly about 10 instructions, give or take, 11. All right. And every instruction now, to make life easier, like NEOS, is encoded in 8 bits. Everybody okay with this? Now, the register names are going to be called K0, K1, K2, K3, to confuse you. Right? Not R0, R11. Why they're called K? K is as good a letter as a R, right? There are Ks. And to confuse you now, when I'm going to be showing you every instruction, I'm going to be using R1, R2 as A and B. That is, these are two registers. So R1, R2 are just identifiers. Sorry for making your life miserable right now. R1, R2 means any, R1 can be any of K0 up to K3. You with me on this?
And K0 to K3 are
Registers, yeah. They are my registers, I call them Ks. Why? Because I like to call them Ks. Why do I refer them as R1? Because I need a variable name. This could have been X and Y, okay? Everyone okay with this? Welcome to the world of computer manuals. People will write whatever they want. Whoever wrote this, they were not feeling well that day. Okay, good. And by the time I realized I made this thing, I had to change everything, so that's why I didn't. I'm a bit lazy. Not enough foresight and laziness on the backside, okay? Where was I? Okay, so our first instruction is called add. What does add do? It adds 2 registers. So it takes 2 registers, R1 and R2. Notice that it doesn't take 3 register identifiers, just 2. And what it does is the following. It takes the value of R1, the value of R2. Remember, R1, R2 means any of K0 to K3, right? Adds them together and puts the result back into R1. So this is a 2-operand instruction set. One of the operands is both the source and a destination. This is very similar to x86 in the AMD processors. That's what they have. They only have 2 identifiers, the base instruction set. Now, let's go to the last part. PC becomes PC plus 1, not plus 4. Why? Because the instructions are 1 byte in this machine, not 4 bytes. Okay. The blob in the middle, it's going to be very similar in pretty much, it's going to be almost identical. No, it's going to be identical for all instructions that have it. This is setting the condition codes, the flags. Remember, I told you there's a 0 and negative. These flags are going to be set as a side effect of many instructions. What these say is you calculated some result. I'm looking at the final result. Here's an addition. If the end result happens to be 0, I'm going to set the 0 flag, make it true. True means 1. If it's not, I'm going to make the 0, 0. So you get for free a comparison here, whether the result you just calculated happens to be 0. And you can probably extrapolate that n means the result is negative. You with me? You get that for free. For free means also you get it whether you want it or not. So it's going to happen. So the 0 and negative flag will be set as part of executing that instruction regardless of whether you want it or not. Sometimes it's going to be helpful, sometimes it's not going to be helpful. That's how x86 works too. That's the intention with condition flags. So that's the first instruction. At the bottom, those wonderfully chosen colors show the instruction encoding. 1 byte, 8 bits. The yellow part, this part if you're colorblind, is 4 bits. This is 0, 1, 0, 0. What does that mean? When the CPU fetches something as an instruction, remember I woke up, I'm a CPU, first thing I do, I fetch something from memory to see it as an instruction. I'm going to fetch a byte. If that happens to have this combination at the last 4 bits, the CPU understands that this is an add. It's important for us to know this now because we have to build a circuit that will interpret these bits and do the right thing. We have to tell the data path what to do. Now, if it's an add, what do I need to specify? I need to say which are the 2 registers, okay? Now, there are 4 registers, so 2 bits are enough to specify any of the 4. I need one for my source and destination, R1, the upper 2 bits here, and another one for the second operand, which is only a source. Make sense? So, for example, sorry for turning off all the lights. So if I were to fetch something like this from memory, this is my new. So the CPU is fetching something from memory as an instruction. It's part of the first step of executing instruction. It looks at this and it says, okay, fine. This means this is an add. Right? Just by looking at those 4 bits. What is the add is this, K0. Why? Because this spells 0, 0. And this is K2. So that's this instruction. This is the instruction encoding. Make sense? Yeah.
For here, should n be equal to 0 if R1 is greater than 0?
Sorry?
Like
Oh, there are 2 n, 1 equals 1. Yeah, that's a typo. I don't know how they survived all these years, but you're right. So what your colleague is saying is, come on, what is this? I mean, 1 and 1. I mean, every time people build processors, there is you get the user manual. At the end, there is a section called errata. Did I say this before? Errata means this is what we thought we built, and this is what we actually built. So this will be one of those. Now, how do somebody manage to do that in 10 instructions? I don't know. I did this, by the way. And I'm sure it's copied all over the place, the same thing, but that's wrong. Okay with the instruction definition? All right, let's move on now. This is subtract. This is the second instruction. What is important here? This is very similar to the previous one. It just does subtraction. Okay. set 0 negative. Oh, I didn't embarrass myself. I just say do that. Okay, good. Same stuff. Notice here the encoding. Again, the last 4 bits tell you what the instruction is. This has to be different. Okay, so that the machine can tell that this is a different instruction. It's actually subtract. Again, 2 register operands, same story. Everybody okay with this? This has to be different. Wonderful. Next instruction, NAND. Why is NAND an instruction? Who knows? NAND is a universal operator. If you have that, suppose you can do everything. Maybe with too many steps, but anything. Okay. So far, so good. Almost identical. Structure-wise, it's the same thing, but the operation is different. 2 operands, you manipulate it in some way. Last 4 bits, it's this encoding. Again, different than the previous 2. Questions up to this point?
For the registers, it doesn't care which, like you could do NAND R1, R1, right?
Yeah.
That's fine? Okay.
Yeah. You have freedom to, you have four combinations here, 4 combinations there. There's nothing here that says they have to be different. It's like neons. In every family, there's one person that is, causing trouble. This is the one. Or I immediate 5. What does this thing do? It takes register K1. Notice it doesn't say R1, R2, or whatever. This is not a variable. It is the register called K1. Not K0, not K3, not K2. K1. This is implicit in this instruction. I will explain in a second. So it takes K1, and then it takes an immediate of 5 bits and orders them together and puts the result back into K1. So far, so good. Why is it like that? Because somebody said so. That somebody, which was me, has a reason for that. This is a way to create constants. That's one way to do it in this machine. It's equivalent to the move high, something like that. But it's an attempt to do this. So there is some reason behind it. Don't start thinking about was this a good idea or not. I can tell you it was not, but it's there for a reason, right? So to illustrate what happens if you make this kind of choices at the instruction set. It sets the 0 negative flags as well. It increments the PC, and here's the encoding now. Notice this is slightly different. It only uses 3 bits for the encoding, not 4. These 3 bits have to be different than any other instructions. It actually occupies 2 slots, if you think about that, because the last bit here happens to be part of the immediate. Here's the immediate. Okay. If I wasn't able to explain anything with the 2 slots for the opcode space, don't worry about it. All you need to know is the following. There is no other instructions for which the last 3 bits happen to be all ones, period. Done. We got to build a circuit that does this. That's all there is to it. This is
Would that be mapped to 2 locations in memory though, depending on how the 3rd bit is?
No, because this is, you go to memory based on the PC, you get a byte, you read the byte. This is a value from memory, not a location in memory. And you just say, if the last 3 bits of the value read from memory is this happens to be an ORI. Okay, it's not, this is never part of an address.
So it just ignores the 3rd bit?
What?
So
Yeah.
just ignores the 3rd bit.
It doesn't ignore the 3rd bit. It's not part of what it is. So the puppeteer, the control, when we design that circuit, there will be some part of the function that says if the last 3 bits are 1, 1, this is an ORI. So set the control signals accordingly. Otherwise, you have to look at 1 more bit. Alrighty then. Now, shift left and right, R1, immediate 3. So this shifts any of the 4 registers. So there's going to be a field there, actually the first up 2 bits. That's, you can use to specify any of K0 down to K3 if you wish, up to K3. And then you're going to shift that by up to up to 4 positions. So the immediate 3 is a bit weird semantics. I'll explain. Okay. Sorry for making this a bit more complicated than it is, but this is a fair comment. Long story short, this is a left and right, which you can view that as a positive or negative number. That's where the immediate 3 was coming when I first wrote these notes. But you can view it whatever you want. The semantics are the following. Look at this number, which is a magnitude, okay, 0 to 3, right? And then shift left and right according to that. So I think we've been better to write immediate 2 now, not talking to you today. Maybe tomorrow I'll think differently. But that's what it means, okay? So here is a 2-bit field here. This is an absolute number from 0 to 3, right? And this says direction, left or right. If this is 1, it means left. If this is 0, it means right. That's what the exclamation mark means. And notice that this also uses 3 bits of the opcode, not 4. So there's no other instruction that has this combination, the last 3 digits. And it does set the 0 negative flag and the PC, blah, blah, blah. Almost done, almost done. Let's go to memory operations. Remember, we have instruction and data memory. There is the load instruction, very similar to news. It takes 2 register identifiers. One of them is a pointer to memory. There's no offset here, not enough space in the opcode space. The last 4 bits are zeros. So if you see 4 bits at the last of the instruction being 0, this means load. You take the value of R2, you use that as an address to memory. You go, you get 1 byte, you put that into R1. Okay. So that we're not confused here. If I had this encoding, what does that mean? It means load into K1, K3. So physically, now, this would mean here's the 4 registers, K0, K1, K2, K3. Here's memory, not to scale. There are 256 of those, all right? Wonderful handwriting. What do? I take K3. I use that as a pointer to memory. I get some byte, wherever this is pointing to, and get that and put it into K1. This is what this load does. That's what news does, with just different bit widths. Fair enough? Okay. This does not set the 0 negative flags. Why? Why not? Questions about this? If you were to guess what's the next instruction, store, and it's the reverse of that, right? It has 2 source operands, R1 and R2, and it goes to the memory location pointed by R2 and stores the value from R1. So this arrow changes the direction. You're writing to memory as opposed to reading from memory. Alrighty then? Now we go to the last family of instructions. I think there are 2 or 3, I don't remember. These are branches. These are different than Neosys branches. Neosys branches are like those samples, the 2-in-1 samples. They have a comparison and a change of the program counter. Here, there's no comparison. Everything is based off the current values of the 0 and negative flag. So the idea here is if you wanted to compare if 2 numbers are equal and then branch according to that, first you subtract them and then according to the 0 flag, you branch or not. So this is what this means. If the 0 flag is false, then PC becomes the target address. Otherwise, PC is PC plus 1, fall through. There are 2 parts I want to discuss. What it means 0 is false, and then the target address. As I said, the 0 is false is a side product of the executing some earlier instruction. If you wanted to compare 2 numbers, you subtract them. Because you're testing for being non-zero, this means the numbers were not equal if the result is non-zero. Fair enough? Now, notice the target here. The structure is very similar to news. Yes, please.
What is Z again?
Z is a single bit inside the machine that other instructions except the loads and stores set as a byproduct. All other instructions are calculating a result, right? The add does the addition, NaN does the NaN, subtract does the subtract, okay? So they're producing a result. The 0 flag is set to reflect whether the result is 0 or not. So 0 is true if the result you just calculate happens to be 0. And N happens to be true if the result is negative, has the upper bit set. You get that as a byproduct of executing the instruction. Again, this is not my, there are machines that do this and some that are very popular, like the one that's on my laptop right now. That's how it operates. It has this form. This is called condition codes, the zeros and negative. Notice that the target address is PC plus 1, so that part is common. Like in news, it was PC plus 4, regardless of whether you're taken or not. And then if it's taken, there is an extra offset. So there is an immediate 4 that comes as part of the instruction. That is a signed 4-bit number, so you can branch back or forward. That's what the SC stands for, sign extent.
That would just be the label, basically, right?
Hmm?
That would just be the label.
if you wanted to write an assembler now for people to use, you will provide a nice convenient way with labels so that the assembler will do the calculations. But if you want to say, I'm like hardcore programming, you say, I don't care, you would put the number there. The machine at the end will see a number, will not see the label. This is a convenience that the assembler provides to you. And I think this assembler is even meaner than that. It won't allow you to put the number if you want, even if you wanted to. I don't know why. But.
So you can only jump back 8 or forward 7?
Yeah.
Okay.
Now, I know there are machines that are more powerful than this, but theoretically speaking, this is as powerful as any, right? So there is a, I don't know who, I think I had this discussion with some of you at some point. There is a course, I think it's called Theory of Computation. I took this a long time ago as an undergrad and then as a graduate student. There was a machine, there was some theoretical result that says that if you have a machine that can do the following, take two numbers, subtract them. If the result is negative, go where I'm telling you, otherwise fall through. That is universal. That is, you can implement any algorithm with that. This doesn't say anything about how easy it is to implement an algorithm. It just says you could, in principle. So this machine is universal. You can implement anything you want. It's actually a bit better than that. It's not that very powerful. And depending on what you want to do, this is good enough. Now, nowadays, I mean, you can buy a processor for less than $1 that is a lot more powerful than that. There is a lot of microcontrollers out there who are very powerful machines, just because silicon is not that expensive anymore. But I think this is pretty decent. It's not that bad. I don't know how this will compare to the computer they used to go to the moon. I mean, it would be, I don't know exactly, but I wouldn't be that far away in terms of computation capabilities compared to that. Where was I? The next instruction is this, branch positive or 0, and it does some funky condition based on the flags. Everyone okay with this? Long story short, there is a bunch of instructions. Most important part, there is some portion of the instruction that is the opcode that specifies uniquely what this instruction is. That is a unique combination. Some of my instructions have 4 bits there. Some of my instructions use just 3 bits. Furthermore, the fields, anytime you do have registers, anytime there is a register that's both a source and a destination, always appears up here. And when every time you have a second register that's a source only, it appears on this. This is a nice design, which is stolen from what NIOS is doing, which is stolen from what RISC machines were doing back in the 80s, because it simplifies the hardware underneath. Okay.
Wouldn't BPZ be the same as BZ? Because if you get Z is true, then N is always false. Because 0 can't be positive or negative.
Don't take what I'm going to say in the wrong way. You may be right. At this point, that's not somewhere I want to discuss, not because I don't think that's an interesting discussion. That's not the point. And I admit to you that when I put these instructions there, not much thought went into what I'm going to call the branches. I just put some conditions there because that's not the point. I'm not saying that's not an interesting discussion, and maybe I made a mistake by choosing this one. I just don't want to have that discussion because we're going to get sidetracked. That's not the important point. And again, I don't mean that why you asking that question, I'm just giving you a fair answer, what I think we should be focusing on. Fair enough? Okay. But we can talk about offline, whether it was a good decision. Any other questions? I'll take silence as a no. All right. Now, let me remind you a little bit about digital logic now. Everything is going to be digital. And it's going to be in the, we're going to treat everything as zeros and ones, and we're going to treat everything as ideal components. That's not the reality of real circuits, but when you do digital systems, there's these very nice people that do actually circuit design. To a great extent, they provide you with this abstraction. It's not easy to do these days, but they do that. And so there's layers when you design systems. This is true of the physical world as well. When you build a building, there is a person that is concerned, for example, how many elevators to have. So whoever did buy it, I don't know if there was not enough money, I don't know what was going on. They didn't do, they could have done a better job, but let me put it this way. That person does not necessarily need to know how to build the steel. Maybe they need to understand what are the properties of the steel or whatever, but they don't need to know how to do that. Same thing with these circuits. We don't necessarily need to know how we can take sand, bake it, do whatever we want so we can do the transistors. We can just assume that it works. Okay. So that's the way to approach that for the time being. I'm going to show you the building blocks. Think of this like Legos, and then we're going to connecting Legos together. So the first building block is going to be a register. They're generally going to have the following form. There's going to be a clock. My registers are going to be what the, sorry if I don't pronounce this correctly, edged triggered. So there's going to be a clock. This is going to be a synchronous system. So there's a master clock that goes up and down, up and down, up and down. The way to think about the clock is this. There are moments in time where the clock goes up, for example. This means positive edge trigger. It doesn't matter, it could have been negative. These are the points in time. The rest, how that happens, who cares? Now, what is the idea here? There's a clock. The clock allows the register to change values if it needs to. Now, at any given point in time, this register, for example, has 8 wires that come out of it. This, by just plugging into those wires, you can see what the contents are. You can do this anytime you wish. So this is a combinatorial output. Or it's always there. You can always read the value. Read is not an action. It's just saying, take the wires, plug them somewhere. That's what it means. Electricity flows regardless. So it's not, you don't have to say read, you just use it. You can put an adder there, you can add something to it if you want. Okay. So far so good. If you want to change it, what you got to do is the following. You got to say, I want to write, this will have been on the top like 0. If this is 0, then on the next rising edge, I'm going to take this value and load it in. I'm going to change that. We're going to assume that this is a perfect element. So this happens instantaneously. The reality is not like that. There is setup time, hold time, blah, 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 blah. We're not going to care about this stuff at this point. It's not the point to care about this. That's not our main concern. In the real circuit, you have to care about that at some point. Okay with this? All right. How do you build this? You guys know?
Flip-flops.
Okay. You know how to do flip-flops? Okay. Or at least you think you do? Okay. Good. You go to the supermarket of flip-flops, you buy one, you use it. That's the idea here. I mean, they're called standard library, standard cells. If you're using FPGAs, they're there. Somebody else did it for you. If you want to be a designer for flip-flops, I mean, I'm sure there is a position inside every company that is the flip-flop person. Okay, which they're trying to squeeze as much as possible. All right, and I don't mean that in derogatory terms. I'm just saying every little piece is like a humongous amount of expertise these days. All right, now, next piece of logic is a multiplexer. A multiplexer is the equivalent of like an intersection road. There are 2 cars coming, but there is only one that can go at any given point in time. That's the multiplexer. You have 2 signals coming. You have this box, whatever is inside, who cares? You have a select signal, and select signal is single bit in this case because this is a 2-to-1 multiplexer. And you can select, if the select is 0, this is going to go on the output. If the select is 1, this is going to go to the output. Okay? It's a way to choose. This is a 2-to-1 8-bit multiplexer because it takes 8 bits as the inputs. They're not single bits. Alrighty then. The next circuit is a decoder. The decoder takes a power of 2 and gives you what's called the one-hot encoding of it. That's the term that people use it. Which means it gives you a vector that has as many elements as the power of 2. If the power of 2 is 2, the vector is going to have 4 elements. And at any given point in time, only one is going to be 1. Everything else is going to be 0. Which one? The one that corresponds to the numerical value of the signal. So, 2 input signal, if the value of that signal is 0, 0, both bits, that's going to be 1. Everything else is 0. If it's 1, 1, that's going to be 1. That's a decoder. Questions about this? Okay, you're familiar with it. Great. Now, next thing, register file. Now, this is going to be a composite. We're going to take stuff we already know, and we're going to build a block. But when I do the diagrams, I'm not going to show you every time what it is. I'm just going to tell you what's the block. What is the functionality of this? This is driven by what my instructions need. The idea here is if I look at my instructions, what is the worst case for any single instruction in terms of how many registers has to read and how many registers has to write. The worst case is something like an add where I read 2 values from the registers, and then I write to another register 3. So this is a 2 read port, 1 write port register file. What is the interface? You don't need to know how it's built. I'm going to show you in a second though. You just need to know for the time being how this operates. What is the interface? It has the following. It has 2 read ports. The read port is something that takes an address, a register name, and gives you the value. Look at this. This says register 1, 2 bits. Why 2 bits? Because there are 4 registers. You give me a register name, 0 through 3. Right? After a while, because this is an actual circuit, you can assume instantaneously for our purposes, you're going to get the value of that register there. This is 1 read port. There is a second one. These are independent. You can read any combination you like. You want to read K0 twice, you can read it twice at the same time. They operate independently. These are what we call combinatorial outputs. That is, they don't have nothing to do with the clock. You just give me a value here. In reality, after a while, you're going to get the right value there. You give me a register name, you get the value there. This is for reads. You can read any time, no worries about it. Then there is a write port, so that we can do add. We calculate the sum, we can write back. That is not combinatorial, that is sequential. That's edge triggered. Again, there is a clock. There is a name of the register you want to write. There is whether you want to write or not on the top. And then there is the data you want to write in. So this is a write port. Register name, data, whether you want to write. You're not going to be writing every time. Only when you want to, you're going to say, here's a name, here's data, write. If write is 0, which means don't write, this can be anything. This guy just says, blah, 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 I don't care what you say. Okay. So far, so good? Now, let's build this thing. So now we go inside the box, right? Somebody, let's say we're a contractor, say somebody, I want you to ship me a register file that does this. How? I'm going to show you one design just to illustrate that these are not as, they're not out of your reach. They're very straightforward. And the one nice property for any design is that they work correctly. The next step is we want them to be fancy, right? They don't want them to be very fast. But first step is I want something that works. So this is a 4-register file. So how about we put 4 registers? We just did registers before. There is the register. Every register has a write port and a read port, and also has some signals that are right or not. I'm not going to show the clocks here. There is a clock. This is an edge trigger device. So the outputs are combinatorial, so I can always plug in something on these wires if I want to. This, you can put a value there, but it's going to be written only if this is 1 and next positive edge. So far, so good? Let's do a read port. So let's grab the outputs of all registers together. This is just drawing wires on a piece of paper, drawing lines, which corresponds to wires. Let's grab the 4 sets of wires, and we have them in our hand right now. And I want you to be able to read any of the 4 in 2 ports. So this and that are outputs, and there would be 1 out of 4 choices. Multiplexer, multiplexer. 1 out of 4 choices. Guess what I'm going to connect next? The choices to the choices, right? So now, I haven't put the select signals yet. What I have is I have a circuit, like a data path, think of it, where I can select any of the 4 independently. Next question is, how do I select that? Well, that's part of the external interface, is those ports, right? The register 1 name and the register 2 name. So if you tell 0, 0 here, well, this multiplexer is going to select 0, 0 and give me on the output. At the same time, the other guy can be saying 1, 1, so it will select the 3rd one. These are the read ports. This is a combinatorial circuit, right? It always works. The moment you change that, after a while, you're going to see the right output here. The delay is this. Fair enough? Huh?
Why does it have a clock input for writing?
This is for these guys, and I'm not showing it. It's for the, so you can do writes.
Oh.
Okay? Writes. Now, if I'm going to write, the signal is going to come, the data is going to come from here. So I might as well send it to all of them. So I say, take the data you want to send and have it stand in front of the door of every register. The question is which one I'm going to open now to accept it. Okay. So send copies to all of them. That's what this means. Okay. Now, what do I need to do? I need to say, first of all, here's the register I want you to write to. And second of all is, I really want to write. So you're going to see a combination of some decoder that says, here's the register name. Let's create a 1-hot vector that says it's U, right? Flag raised. Plus an end signal that says, I really want to write, the RF write. That's what you're going to see. This is the register name, 1 hot encoding, only one of them is 1, and gates. And all of them with RF write. Only if you want to write, the one you want to write is going to get the value in. This is the write signal of the register. Fair enough? Here's the register file. Is this the best register file in the world? It's our register file, we love it. It just works. That's what it is. Is this how people are going to build register files? Conceptually, yes. In actual circuits that have 32 registers or not, you have to know about SRAMs and how this is done. These things are embedded in the design. I mean, there is literally a multiplexer or whatever, but it's not done like this. It's part of there's a bit of analog stuff. What did I mess up?
What's different between the decoder and the
Decoder takes a power of 2 and expands it into a vector and gives you which one it is. It's like an indicator light. Yes, that's the definition of a decoder. Fair enough?
Multiplexer just.
Multiplexer is, I have 4 choices, which one gets to go? So you have people saying, no, choose me, you say, you go.
Isn't that the decoder as well?
No, decoder says, here's a power of 2.
Okay.
Here's a different representation of that, one vector. So you give me a number, and I have a lot of indicators there, I light up that. Notice this guy has 3 signals coming, 2 inputs, 1 output. This has 1 input, 1 output. Groups, of signals. 1 signal coming in, 1 group of signals coming out. This has 1 group of signals, data, 1 group of signal which is select, 1 output, data passes through. Okay. Now, I really wanted to have time to describe what does this look like to you? Exactly, that's what it looks like to me, like a pants, right? You're like a broadswords or something like that. So sideways pants. This is short ones. I guess if these are not short, the dimensions of the person are a bit weird. So this thing takes 2 inputs, A and B. It takes a control signal, and it can do any of the calculations that our machine needs to do, addition, subtraction, NAND, whatever. Right? And it gives you the result as the output, and also it sets the 0 negative flag. This is called ALU, arithmetic and logic unit. Logic means bitwise. Now, I think there is enough time to design this to this level. This is it. What does the machine need to do? It needs to do any of these 1, 2, 3, 4, 5, how many? 6 things. What does the ALU do? Whatever, grammar, whatever. What does this thing do internally? It does all of them. Okay, why? Why not? If you don't care about power and energy, sure, just calculate everything. At the end, what does it do? It selects 1. Okay, they're not power of 2, so what? These are not connected anywhere. 0 negative flag, that's what it is. 0 means the NOR, and negative is just the upper bit. Ta-da, we just designed an ALU. Okay, now, granted, you know how to do NANDs, you know how to do the ORs, do you know how to do adds? You probably did half adders, full adders, look ahead, blah, 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 right? Subtract is, you have a non-subtract? No, look ahead, that's okay, this is a design optimization. It's interesting to do at some point, but many things are interesting. I can tell you how to do Musaka too, that's very interesting too. There's only so much we can do this clock. Multipliers are very interesting as well. There's only so much in this lecture, right? So we're not going to do that. What was I? Subtract is XOR plus 1. That's one way to do subtract. So far, so good? Now, we have 5 minutes left. And rather than taking your time by telling you about the instruction memory, which, by the way, would be something like a big raster file. Anyway, I'd rather talk about it's only 256. And that's how memories are built, but they're a bit more clever than that. I want to talk a little bit about the midterm, and I want you to decide whether you want to take it or not. What am I doing?